Hey there, astronomy students. This is Mr. Lark. We're on part B for this podcast 7.1 for Starlight and Atoms. All right, so picking up where we left off on the last one, just a couple more things to go over with this. A Balmer thermometer is going to be used to detect absorption lines from atoms that have electrons in the second energy level. So the reason why the cooler stars won't be able to be detected is because they have few violent collisions. They don't have a lot of excited atoms. They have most of their atoms in the ground state. And if they're in the ground state, they can't absorb photons so that they get excited. The hot stars, on the other hand, have extremely violent collisions, and they knock electrons out of the atom or up to much higher energy levels. And that means that the electron's not going to be in the second energy level. The medium absorption or medium temperature stars will have those collisions, and they'll have plenty of electrons in that second energy level. And so that's why you'll be able to pick up the temperature or pick up the strong Balmer lines with the medium temperature stars. Balmer lines are used to determine the temperature of the star. So if it ends up having a strong strong hydrogen line, right here, strong hydrogen line, then typically the temperature of the star is going to be roughly about 10,000 Kelvin. If it has a strong iron line, so here's one here and there's another one here. If they have strong iron lines, typically it's going to be anywhere between or around 5,800. If it has strong helium lines, look up here, it's going to be 20,000 or more. And if it has strong TiO, titanium oxide lines, here it's going to be an extremely cold star, or cooler star, compared to the others, and it's about 3,000 Kelvin. And the reason for that is because once you get past helium and hydrogen and you start bonding to make, well, not bonding, but in order to make elements higher than helium and hydrogen, they have to fuse together. And those fusing of those nuclei ends up producing some of those higher, those heavier elements, such as carbon, and then they keep fusing and fusing, and you'd end up with your calcium, and then you end up with your iron. Well, once you get to iron, it's fusing now to form those even bigger elements that are much heavier, and then you end up getting your bonds. Well, the bonds happen because these atoms are smashing into each other, and if it favors bonding, which means it's the right temperature and it's the right pressure, it's not too hot, and it's not too cold, that you're going to end up getting compounds such as titanium oxide. And once you start seeing compounds, and you see compounds forming and showing up in these spectral lines, you know that it's a cooler star because the hotter stars don't favor bonding. Our star is around here. It's at about 5,800, so it's not a really hot star. It's actually a pretty cool star if you think about it. Hey, that's right, it is pretty cool. All right. Okay, bad joke. Moving on, spectral classification. Okay, we'd watched a video. Annie J. Cannon was the first astronomer to work on this classification system. Okay, remember she was the one that was she was deaf, and she was working on. They would get different pictures of them, and she would put them into major classes. So there's 7 major classes: O, B, A, F, G, K, and M. O being the hottest, and M being the coolest. And then each one of those classes has a subclass, and the subclasses would be numbered 0 to 9. So let's say that we were in the F range, and it would be, you would have your subclasses F0, F1, F2, F3, F4, F5, F6, 7, 8, 9. Right? Recently, they have just started to identify others back in I think the 90s and 2000s, where they ended up finding the L dwarfs and the T dwarfs. So something new that we can look at. Yay! All right, composition of stars. So Cecilia Payne, she came over from Britain or Europe, one of the two, I cannot remember, but she came over and she studied at Harvard. Now, Harvard wouldn't give her her degree because at the time they wouldn't allow Harvard women to be students at Harvard. So she actually got hers from Harvard, but it was through another school, and I can't remember what the school's called. But she did her thesis work on the strength of absorption lines and how they relate to physical conditions of atmosphere and stars. So what does that mean in English? Well, that means that she was able to show that over 90% of the atoms in stars are hydrogen. And then she also showed that most of the rest of the atoms, the other 10%, about 9.5%, 9.9%, are helium atoms. Okay, the heavier atoms, calcium, sodium, and iron, seem to be the most abundant ones because they're better at absorbing photons at high temperatures in the stars. Okay, but the problem was, most people believed that at the time. However, they didn't believe her. They said she was wrong, and the reason they said she was wrong is because hydrogen lines don't show the most. They're the least visible in most spectra, and the helium lines are completely invisible in all but the extremely hot stars. Okay, so it didn't happen until 1929 when they recognized that, hey, she was right. See? Leave it to a woman, right? Oh, yeah. Okay, sorry, boys. Okay, moving on. Doppler effect. So, Doppler effect is going to be an apparent change in the wavelength of radiation, and that's caused by the motion of the source. So, the wavelength of the radiation that's coming off seems to be moving or changing because the source is moving or changing. Okay, and this would be used to tell us how quickly the distance between you and the source is increasing or decreasing. All right, so you've all heard an ambulance or a fire truck or a police car drive right by, right? And as it comes up really close, or NASCAR races, right? So as the car comes close, it gets really high pitched, and then as the car goes away or the siren goes away, it gets really low pitched. So you're watching a NASCAR race, and the car comes flying by, goes, right? It gets really high pitched, and then it gets really low pitched. All right. Well, the reason for that is because, well, it's the same thing in stars. Let me do it in stars. It'll be easier. All right, so the wavelengths of the light will get shorter as the object is approaching us, just as the pitch of the sound gets higher, which means that the wavelengths are getting shorter as the object approaches you. Once it gets past you, the wavelengths are going to be longer. So in light, we say that it is red shifted and blue shifted. Okay, so a star approaching the Earth is going to make a shorter wavelength. The wavelength is going to be shorter. Blue light has a shorter wavelength, so we say it's blue shifted. So here's our normal. Let's see if I can find a different color, because I don't think this color's going to work. Here we go. All right, so this would be our normal spectrum. But if the object is approaching us, look, it's shifted. And which direction is it shifted? It's shifted towards the blue, and so they say it's blue shifted. Okay, well, if it's red shifted, that means it's going away from us. The wavelengths are going to be longer. It's going to take more time for them to reach us. Okay, so it shifts towards the red. And that's how they use the Doppler effect to determine the distance or how something is moving. All right, so in a spectral line, we can determine a lot of it not just from the intensity or how high the line is, if it's shifted and this and that, but we can tell by the shape of it. Okay, so the shape of the line, if the width of the line is what we're looking at the most, that's the most important thing. And the natural width of the line should be anywhere between 0.001 nanometers and 0.00001 nanometers. Okay, now that's the normal width. That's pretty small. The broader lines can actually be used to help us determine a star's rotational rate, a star's temperature, and a star's density. Okay, because if the star is spinning rapidly, the Doppler effect will broaden those spectral lines and make them bigger. Okay, if a star's temperature is cooler, the Doppler shift will go down, and if it's hotter, the Doppler shift will go up. Well, if there's a larger Doppler shift or change in the Doppler effect, then it's going to give us a wider line. Okay, and then for the last one, for the density, it's based on collisional broadening. So it depends on how thick the gas is. If the gas is dense, you're going to have more collisions, and the more collisions you have, the wider the lines are going to be. Okay, so it's all just different things that you can pull out of these spectral images that we're going to be looking at. All right, so here's an example of the Doppler shift. I thought this would be really nice to see. Okay, so as the star is rotating towards us, we're over here looking. As the star, let me change that color again. All right, as the star is rotating towards us, okay, as it comes towards us, you'll notice that the this is where the line should be. Okay, and it's all the way to the right. It's been shifted, right? And it's red. And then as it goes away from us, it's going to be, I'm sorry, it's blue. And then as it goes away from us, it's shifting again and it's turning towards the red. Okay, so it's just another way to look at this Doppler shift. Yeah. All right, so here we go. I couldn't help myself, Sheldon Cooper, when he shows up as the Doppler effect. I had to do it. All right, I'll see you in class on Monday.